Removable discontinuity. So the first thing that we're going to do is we're going to graph the function f of x, where f of x is x squared minus 5x plus 4 divided by x minus 4. So to graph something like this, I always like to factor it. So to factor our numerator, we would have, let's see, x minus 4 times x minus 1, and we're dividing by x minus 4. And you can probably see what's happening already. We have a factor of x minus 4 that we can remove from our equation. We can just say it cancels out, it makes a 1, but I really want to use that word remove. And then what we have left is f of x equals x minus 1. So that's really easy to graph. So we'll start at -1. Our slope is 1. And we'll get a few points on here. And there we've got a graph. But you should be stopping me at this point. You should be saying, but what about that x minus 4? We know from other math classes we've taken that we can't just forget about that. That's always part of our restrictions on our domain. We would have to say here that x can't actually be equal to 4. So you might remember doing that like in algebra 2, where you simplify and you say, yes, the answer is x minus 1, but x cannot be equal to 4. We did that a lot in algebra 2. So how I fix my graph then is I go over to where x is 4. So x is 1, 2, 3, 4. Trace it up to my graph, and then I create a hole at the 4. So the graph can exist everywhere else, but not at 4. So that's why we have removable discontinuity. If I remove that factor, if I remove the hole, I now have a continuous function. That's the only thing standing in our way. So let's go through and just work out some of these different limits and see how it compares on this graph. So the limit of f of x as we're approaching 4 from the left, so that would be this direction. This would be limit as x goes to 4 from the left. Well, it's getting really close to, let's see, y is 1, 2, 3. So it's getting really close to 3 for y, so we're going to write equals 3. As we go from the right, so here's our limit as x goes to 4 from the right. Same thing, we're really close to 3. We can't quite get to the 3. We can't have that point 4 comma 3 on the graph, but we can get really close to it. So because these two match, because our limit as x goes to 4 from the left and the right are both 3, then we can say the limit of f of x as x goes to 4 is just 3. But now here's the trick. F of 4 itself, well, that would be 4 minus 4 over 4 minus 1. We have to go back to that original function f of x. Doesn't work. That one does not exist. It's undefined. Using the way we've been doing limits in class, the way I would have figured out this limit rather than using some of the formulas that they have done is I would have started here. I would have crossed out my common factor. And then if I wanted to find the limit as x goes to 4 of f of x, then I would just substitute in here. And I would write 4 minus 1, and then I have equals 3. So that's how I'd work it out if I was actually trying to find the limit, not with a graph, but just with algebra instead. So I know there's one example in the textbook like this in 12.2. So maybe we should label this example in 12.2 in your Glencoe textbook. But it's worth taking another look at that. So on to what a non-removable discontinuity is. So non-removable is going to be any other kind of discontinuity except removable. So what we're working with right now is jumper infinite. Those are the two main types that I see when I look it up and I do searches. I find other kinds of discontinuity also in higher math. They're a little more it's just more advanced than what we're doing right now. But this year we're working with jump and infinite. So jump is when you have maybe a graph and it stops here and then it starts up here and it does some other stuff. That's going to be jump. And we usually see that with piecewise functions. So we'll make a note of that. So the graph is actually jumping. And it's most often seen with a piecewise function. Oh, got to go back to the pen. Piecewise functions The other place that you'll see that is there's some weird absolute value equations. So not the absolute values that we like to graph that remind us of parabolas, but like weird absolute values where you have like x in the numerator and denominator. Infinite is just going to be when your graphs go off to infinity, like that. So think like reciprocal graphs. Anytime you're going to have rational fractions, rational equations or fractions, that's going to be something where you look at infinite. So let's erase this now. So we'll write, think about things. Think about things in the denominator. That make a 0. So if I wanted to create an equation that had both removable and non-removable, I could take my function from the other page, x minus 4 times x minus 1 over x minus 4. The fact that I can cross this out makes it removable. If I want to have one that's also not removable, I could just add another factor in here, and I could write x plus 2. Now I have a function with one removable and one non-removable. That's kind of messy. Discontinuity. I hope this helps. Let me know if you guys have more questions.